Okay guys, and here we go with the start of part 2 of our 12.2 notes for geometry here. Moving on into theorem 12.7, and again, it's a converse right here because once more we have that magical phrase of if and only if. And this one says that within one circle, or congruent circles, two chords are going to be congruent if and only if they are equidistant from the center. Equidistant is one of those words that has shown up periodically during the course of the year here in geometry. And so the meaning of it right there would be, just if you just break it down, equal distance. So if we had ourselves a circle, just kind of draw a big one, pretty ugly one right there. We've got the center of our circle located right over here. I'm going to draw one chord, I think, in purple. And I'm not really going to pay too much attention to this one right here. Okay, so there's our first chord right there that I've drawn in purple. And I'm going to draw a second chord. And if you're taking any notes here on your own, I wouldn't draw this one just yet. But I'm going to draw a chord here in red that's closer to the center of the circle than that purple one. I want one that goes almost right by it. And there we go. Now, two things that I want you to conclude from this. First of all, the red chord looks like it's closer to the center than the purple chord was. And the question I would ask you guys is, since the red one is closer to the center, do those two chords look like they're the same length? And I think the answer to that is no. The red one looks like it's longer than the purple one. Now, if I did the opposite, if I drew a chord way the heck down here that was farther away from the center than the purple chord was, now what I think you would notice is that this second chord right here looks like it's going to be shorter than this chord right over here. So the chord that was closer to the center is longer, and the chord that's farther away from the center looks like it's shorter. Okay, that's kind of a mess I made of this diagram, so let's go back and do this right. All right, so now in just a second here, I'm going to switch back to purple. And since I drew this by hand and I didn't draw it very well, I'm not sure how this is going to work out. But if we measure the distance between the center of the circle and this chord, which we always do with a perpendicular line segment here, if I tried to do the exact same thing down here, so, okay, about like that, all right? And if I now try to draw the perpendicular line segment through that endpoint right there, okay, what should happen here, and I don't know that it worked out perfectly here, is that if these two chords right here are equidistant from the center, meaning that this line segment is congruent to this line segment right here, the two chords are the same distance away from the center. And that should mean that the two chords would be congruent. Now, it's going to get messy to use tick marks for that. So I'm going to go ahead and put an X right here for the length of that chord on top. And then I'm going to put an X right here for the length of this chord down here on the bottom. So the only way that these two purple chords can be congruent to each other is if they're the same distance away from the center, which we would need these tick marks here and here in order to show us. Okay, moving right on, theorem 12.8. I think that's one we'll figure out okay without necessarily having an example here. Okay, theorem 12.8, in a circle, if a diameter is perpendicular to a chord, then it bisects both the chord and its arc. All right, I like this theorem a lot. So let's take a look at the if. The if says we have a diameter perpendicular to a chord. Well, we can't have any of those things without starting with a circle first. So we'll draw that. The center of my circle is going to be located right about here. And going back to the if, I want to draw a diameter that's perpendicular to a chord. So the first thing I'm going to do is start with the chord. All right, just connecting two points on the circle itself. So there's our chord. And we now want to draw a diameter, meaning it has to pass through the center of that circle. But we want to draw the one and only diameter that passes through the center that's perpendicular to the blue chord that we just created. So if I did this, that's not very good because that does not look like a right angle right there. So I needed to be more careful about how I did that. The only diameter that we can draw passing through the center, perpendicular to the chord, should look something like that. Boy, my lines are not very straight today, guys. Sorry. Okay, but the key here is that we wanted this to be a right angle. Okay, and if that happens, now let's go to the conclusion of the theorem. It tells us that the diameter that we just drew bisects the chord and bisects its arc. Okay, so let's switch to green right here. So if this happened, that now tells us that the blue chord got bisected by this green point right here. So this segment on the left has to be congruent to this segment here on the right. And it also tells us that this arc up here on top had to get bisected as well. So if this little arc over here has a length of S, that one has to have the same length of S as well. So that one perpendicular chord there is going to bisect both the chord and its arc. All right, let's see this one as an example right here. This is a tough problem. They tell us here that R is 65, and one thing we should be used to here, guys, is if they just randomly throw out the variable R, we're talking about the radius of our circle here. So the radius of this circle is 65, and the question here is, are line segments AB, this one right here, and AC congruent to each other? Well, AB and AC represent the distance from the center of the circle to their chords, okay? And we want to know if those two segments in yellow are congruent. Well, Theorem 12.8 says that those two segments are going to be congruent if and only if, right there, we are bisecting the chords and the arcs within this circle. So the real question becomes, what's going on with the lengths of those chords? So let's play around with that right over here. Okay, first thing we can deal with right here. All right, let's see where we're going to go with this one. Switch to red right here. All right, now AB is not a radius and it's not a diameter, but if we were to extend it just a little bit past there and a little bit past here, you can make a diameter out of AB. All right, so just having that little piece of it is good enough. And the important thing here is that AB is perpendicular to that chord. That means that it has to bisect that chord. That's going back to Theorem 12, I lost it right here, guys, back to Theorem 12.8. So since this big chord on the top had a length of 120, it gets cut in half, and I know that each of these pieces right here is going to be 60. Okay, the next important thing I want to take advantage of is the fact that the radius of this circle is 65. And one habit that I've gotten into over years and years and years of teaching geometry is to realize that it's always a good idea to draw a radius from the center of a circle to the end point of a chord. And that radius that I just drew in red, they told us had a length or a measure of 65. And now if we take a look, we have just formed ourselves a right triangle right here with a leg of 60 and a hypotenuse of 65. So what I want to do, switch colors on you here, I want to try to figure out how long this piece is right here. So because it's a right triangle, we can use the Pythagorean theorem. X squared plus 60 squared, that's leg squared plus leg squared, equals my hypotenuse, which is 65 squared. Okay, let's see what we got right here, guys. X squared plus the 60 squared is going to be 3,600 equals, and I think that 65 squared is going to be 4,225, but I feel like I should maybe check that. So hang on just a second here, guys. No, not there. No, not there. Calculator's here somewhere. Well, we'll run with that and hope that that's right. Let's see what we got here. So subtracting the 36, I believe we're going to get x squared is equal to, that's going to be, yeah, that worked out, 625. And we'll take the square root of both sides right here and get x is equal to 25. Okay, so that's important here, guys. This x, let me get rid of that guy and just move it out of the way right here. We know that the length of that piece right there was 25. Not incidentally, that's the same as the length of AC right over here. So I think we've answered the question here, guys. The question was, are AB and AC congruent? Well, we just found that AB was 25. We knew already that AC was 25. So the answer to this question is a big old yes. We know that AB and AC have to be congruent because they both have a measure of 25. Okay, moving right along right here. Theorem 12.9. In a circle, if a diameter bisects a chord, then it has to be perpendicular to that chord. So again, just flipping around parts of that last theorem right here. So if we have a circle, we want a diameter to bisect a chord. So I'm going to draw a chord over here on the left-hand side. Okay, looking something like that. Our center would be located roughly around here. And what we want is for a diameter now, something passing through the center, to bisect that chord. And if it does, this theorem tells us that it has to form a right angle. So it wouldn't be very good of me to draw a diameter like this, because it really didn't bisect that chord right there at all. So I've got to be careful. And bisect means passing through the midpoint. So I would need tick marks right here to show that that red dot is in fact the midpoint of that chord. And now there's only one diameter that passes through this midpoint here that also passes through the center of the circle. And it would look roughly something like this. And I drew this by hand so it doesn't look great, but the conclusion of this theorem is that that diameter that we just drew would have to be perpendicular to that chord. Okay, so that's what theorem 12.9 tells us. And then theorem 12.10 right after that, in a circle, the perpendicular bisector of a chord has to contain the center of that circle. And this can be kind of useful if you ever had yourself a circle and you wanted to try to find the center of it, but you weren't sure where it was. The perpendicular bisector of a chord has to contain that center. So if I drew a chord that looked, I don't know, maybe something like that, and if we could come up with the perpendicular bisector of it, well, let's see what that one would look like. Bisector means that it has to pass through the midpoint of the chord. Okay, so again, tick marks right here and here are going to show that that red point is in fact the bisector. Now, one of Euclid's basic postulates of geometry, there is only one line that we could draw that passes through that red dot that's perpendicular to the purple line. So if I drew this very, very carefully, okay, maybe something like that, that this segment that I just drew right here is the one and only perpendicular bisector of the chord that we drew. Well, this theorem tells us that that chord that I just drew in red has to contain the center of the circle. If we wanted to be really specific about it, the center of that circle would be located at the midpoint of that red chord, which I'm going to guess right now is located right around here somewhere. And that's a way that we could locate the center of a circle. You could draw any chord, find its perpendicular bisector, and then realize that that you just drew in red is a diameter of that circle. Find the midpoint of that diameter, and then boom, you have your center. Okay, everybody, I wasn't going to do examples on those last two. That was a really long section. That's why we split it up into two parts in our notes. So let's try the 12.2 worksheet and see how we do on that.